In this lesson, we're going to make sense of the following. Consider the double integral over the region in xy of the function f of xy, and we'll just say dy dx for short. Okay, in doing this double integral, suppose we make a transformation where x is going to be some function of u and v, parameters u and v, and y is going to be some function of u and v. So we're transforming x and y into u and v. In doing that, we're going to have some transformed region over uv of f of x of u and v, y of u and v, and then we have this symbolic notation par xy over par uv, gulp, du dv. Now, there's this thing called the Jacobian, or J for short. And the Jacobian is this mathematical notation, par xy over par uv. One way to memorize how to perform this operation is to do a 2x2 determinant of the following: par x, par u, so I'm doing all the x's first, par x, par v, in that order, and then along the bottom would be par y, par u, par y, par v. And if we do the determinant here, we get par x, par u times par y, par v minus par x, par v times par y, par u. And remember, the goal here is to make some general sense of this. Quick note on this: the way that we show it initially is that this notation can be written like the determinant, and then the determinant yields this mathematical operation. But the truth is, the concept lies here. And then we invented this to help us remember the mathematical operation. And then we use this notation to simply express that we ultimately want this mathematical operation. I would like to point out here that these two bars here are not for a determinant that's actually absolute value. So we perform the Jacobian, and then in this formula we import the absolute value of the Jacobian here, or should I say here. Now, before moving on, I want to talk about a specific transformation. One is very common, which is a polar transformation. Now, this polar transformation is something that we've done several times. The T is for transformation. X equals r cosine theta. See, we're converting x into terms of two different parameters, r and theta, and y is r sine theta. In this case, the absolute value of the Jacobian is the absolute value of this operation par xy over par r theta, and we're going to show that that comes out to be r, and that's always the case under the polar transformation, and we will prove that before the lesson is done. Now, I'd like you to think of this absolute value of the Jacobian as a converter, something that links a set of variables into another set of variables. And to illustrate that point, we're going to move on to the second thing here, and this is the beginning of trying to make sense of all of this. We're just going to call this number 2 because it's the second thing we're doing. And I want you to look at this regular integration problem, f of x dx over some bounds of x. And what we do in a u transformation, or a u substitution, we then transform over x to now over u, and we convert f to be f of x of u. Now, this is not the traditional approach of u substitution, but you're going to see here that we need this linking portion here, the dx du, and then ultimately times du. This is the U substitution method. Okay, let's do a U substitution problem just to kind of prime us for what's going on here. So 1 over 2x plus 5 dx, we're going to take the integral of that with respect to x. Okay, in the traditional U substitution, or at least the way that I taught it, U is equal to 2x plus 5, and then du is 2 dx, and then dx is du over 2. So when we make this transformation here, we have 1 over u, and then dx becomes du over 2, and this is a review for you. And we pull out the 1/2, and now we have the integral of du over u. And then when we integrate that, we take the natural log of absolute value of u plus c, and then we convert this back to x. So 1/2 natural log absolute value 2x plus 5 plus c. So that's a approach, maybe a more traditional approach to the U substitution. Now let's do the same example except using the transformation approach. Okay, in the transformation, we're going to start off by saying u is 2x plus 5. Then I'm going to solve for x in terms of u, and so that's simply going to be u minus 5 over 2. Then I'll need this converter piece, dx with respect to u, and dx with respect to u is simply 1/2. And so now this integral over x, 2x plus 5 dx, is going to be the integral over some bounds of u. And if I look at this specifically, it says f of x of u. So that's going to be 1 over 2. This is a function x of u. And so this portion here is u minus 5 over 2 plus 5. And then we need this transformation, or Jacobian, and that comes out to be 1/2, and then du. And if we work that out, it comes out to be the same. 1/2 the integral over u, 1 over u du, which is exactly what we did earlier. And of course, that's 1/2 natural log absolute value plus c, which is 1/2 natural log 2x plus 5 plus c. That's leaving the bounds indefinite. Okay, in just a moment here, I'm going to have you refer to your notes packet where you're going to complete the warm-up. Now in the warm-up, I just want you to set up the integral, and that integral is one that represents the volume of a solid, and that solid is bounded by z equals 4 minus x squared minus y squared and the xy plane. Again, I just want you to set up the double integral that would give us that. I want you to think of z as f of xy equals 4 minus x squared minus y squared. Okay, it is now time to press pause to complete that task. Okay, this shape here makes a paraboloid facing down. So this traditional 3D shape that goes like this, and then it intersects the Cartesian plane at a circle. So if I look at that projection, if I go xy, x-axis, y-axis, and I see where this paraboloid intersects the Cartesian plane, we see that we have a circle here with a radius of 2. Now we set up the double integral. So the volume is going to be the integral, the double integral. Okay, so we have to fix either the x or the y. In this case, I'm going to fix the x. Now if I fix the x, I have from -2 to +2. So -2 to +2. But then we sort of have a problem here. This is only a type 1 region if we break this circle into two functions. One function on the top and another function on the bottom. So the circle has the equation x squared plus y squared equals 4. And if we're solving for y, y is going to be plus or minus the square root of 4 minus x squared. So that gives us our two functions that we need. The yellow function, the one on the bottom, would be negative square root of 4 minus x squared. And the top function, which I'll put in pink, is the positive square root of 4 minus x squared. And of course, we're taking the integral of the function, so 4 minus x squared minus y squared, and my order was dy dx. And you could see how complicated this could become with these radicals. It's not always impossible. Sometimes it's impossible. But you can see that this is going to be quite taxing to perform this integration. Now this leads us up to the fourth part in the notes, which is to evaluate this integral using a polar transformation. Okay, so if we do a polar transformation, obviously x is going to be r cosine of theta, and y is going to equal r sine of theta, and our absolute value of our Jacobian, which is, again, par x, y over par r theta, that's going to come out to be the absolute value of r, which is always r, which we said we're going to prove later. Okay, so now, why do we make a polar transformation? Well, you could probably see here that this region that we're integrating over is a circle, which is considered a polar region. So it makes sense to do a polar transformation. So our double integral, which goes over x, y initially, like we did here in the warm-up, of 4 minus x squared plus y squared, notice the way that I wrote that, dy dx. Now we're going to make this transformation. Okay, so first let's do the inside. So 4 is 4 is 4 is 4 minus, now x squared plus y squared, if we in fact make this transformation, that's going to come out to be simply r squared. So that's the integrand, but we cannot forget the Jacobian. Remember that transforming piece, which in this case is r. Then we have dr d theta. Now we have to talk about the bounds, and these bounds are set up the same way they were last year. So over theta, we're going to go 0 to 2 pi, and then r is going to go from 0 to 2. Now this is also pretty desirable because the bounds are what we say rectangular. Even though this doesn't look like a rectangular, the fact that the bounds are fixed, and if we put this on a new plane, let's say the r and theta plane, well then r goes from 0 to 2 and theta goes from 0 to 2 pi, and it does in fact create a rectangle, and that makes integration very easy. Please consider pressing pause and doing the integration on your own. I'm going to try to move somewhat quickly through this. 0 to 2 pi, 0 to 2. I'm going to first distribute the r. Okay, next I have to integrate with respect to r. 2r squared minus r to the fourth over 4. First, we'll indicate our transformation. X equals r cosine of theta, y equals r sine theta. And the absolute value of the Jacobian will equal r. Our integration becomes the integrand, which is e to the negative r squared, the Jacobian r, dr d theta. So I'm going to fix theta to go from 0 to pi over 2, and r is going to go fixed 1 to fixed 2. Now let's prove that the Jacobian under the polar transformation is always r. Keep in mind, we haven't really discussed what the Jacobian is on a larger scale, but assuming that we know how to compute a Jacobian, at least a 2 by 2 Jacobian, will do the process. Okay, this is going to be the determinant of par x, par r, par x, par theta along the top, and then par y, par r, par y, par theta on the bottom. So let's do those particular operations. This is x and this is y. So the partial derivative of x with respect to r is the cosine of theta. The partial derivative of that x with respect to theta is going to be negative r sine theta. Now let's do the y function. The partial derivative of y with respect to r is the sine of theta, and the partial derivative of y with respect to theta is r cosine of theta. Now if we do the determinant, we have r cosine squared theta minus a minus, so plus r sine squared theta, and you see that that comes out to be r. And then the absolute value of the Jacobian is the absolute value of r, which is simply r for r greater than 0. You might notice that we could have switched the r and the theta here. There's no reason we have to do it in that order, in which case the Jacobian would have come out to be negative r, but when we take the absolute value of it, it comes out to be positive r. Now you are likely asking yourself several questions. You probably understand that this is the linking operation in a U substitution. However, you're probably trying to wrap your mind around how this operation is the linking function for multivariable transformations. And that's a fairly tall order to tackle, and we will attempt to do this in the third part of this lesson. For now, we just know that this is the linking operation, and we know that this is denoted par x, y, par u, v. And this one is what it is. The next question you may be asking yourself, why do I need the absolute value of this? And we will also tackle that in part 3 of the lesson. I'm also going to give you a preview that provided certain conditions exist, the absolute value can also be written around this operator, although we don't normally do it, and I'll show you why in part 3 of the lesson.